Greetings and welcome back. So we finished our preliminary examination of the theory of elasticity. There's much more that we could do, and I regret that we were not doing more, but as it is, I'm probably already outwearing my welcome in this course. What we're going to do now is we're going to turn to Newtonian fluids, to sort of the next layer in the progression of field theories of matter, because what we're doing is we're trying to work our way towards the full story of active matter. So the progression is linear elasticity, which we've already done. Then we're going to do the Newtonian fluid, which is the fluid mechanic analog to my mind, because it's like the elemental example of a constitutive model for a fluid. And then we're going to put elasticity and viscosity together in the form of a simple treatment of viscoelasticity in one dimension, in which we think about the shortening of junctions between cells and tissues. That'll be a lot of fun. And then that will embolden us to think about the full problem of active matter. So Navier Stokes is sometimes goes under the name of hydrodynamics, of a Newtonian fluid. And what we're after is we want to get the full governing equations. And really, the way I want you to think of this is, I'm going to say this is nothing more, I'm going to put that in quotes, than F equals ma. The reason I put it in quotes is because, the Navier Stokes equations are hard, and there's a prize, a mathematical prize, for somebody who can even solve them. So, in generality, it's really hard stuff. But what we're going to do is I'm going to do my absolute best to present it as an F equals ma problem, where we're trying to just implement what we already know about dynamics, maybe from point masses and planets and that kind of thing, and now think about how we might generalize that to the case of a continuum fluid. So I guess I just want to start by saying a little bit about the domain of inquiry of hydrodynamic theories, at least for the start, for what we're going to think about here. And what I'm saying is that, if you were thinking about motion in the atmosphere or motion of the ocean, clearly the densities of these two are not correct. In other words, the representation on the right is making it seem as though the atmosphere has a similar density to the water, which it clearly does not. But there's a factor of 1,000 difference there. And then at the bottom, two pictures that I really love. One of those is from Indonesia, and it's just, you see these really interesting patterns. And then the other is off the coast of Baja California. And, you see these downstream wakes and vortices being shed off of this island. I think that's Cedros Island, if I'm not mistaken. And maybe not. No, I don't think it is, actually. But so, okay, so we're interested in, trying to think about how we would account for the motion of these kinds of fluids. And what we're going to do is we're going to exploit the continuum theory protocol. So let me just remind you of what the concept is, and this is what we're going to do. So 1, identify the field variables. And as I already say down here, my first stab at the problem is to say that V of R and T is it. Those are kind of notes to myself from previous iteration of thinking about things. So what we're going to say is that we have a velocity vector field. What that means is that every point in space as characterized by the vector r, there will be a velocity. The velocity is a vector, which means I'm going to have to assign an x, a y, and a z coordinate. And you can see that I'm going to use the initial notation that I gave a homework about and that I already gave a bit of a discussion of. So the idea is we have the continuum theory protocol, we identify the relevant variables, then we're going to impose the conservation laws, which in my case is going to mean, add up all the forces. And what you can see down here is that we're going to have the equivalent. Here's the F equals ma. So on this side, we have the F, and it's the force per unit volume, so it's really the force density. And then on the left-hand side, this is the ma. So rho gives us the mass density times dv by dt, which is the acceleration. So this is the balance that we're going to do. So we're going to sum up all the forces on that little cube, and an alternative interpretation would be that we're going to compute the flux of momentum out of the little box, and those two are going to be equivalent. The next point is we're going to infer, measure, or guess the constitutive law, as usual. And here I write the equation for a Newtonian fluid, which tells me how shear stresses are related to gradients in the velocity. So we'll come to that. Once we have the constitutive model and we have the balance law, we put them together, and out of that emerges these apparently innocent-looking governing equation, which really are incredibly hard to solve. So that's what the continuum theory protocol is going to amount to for us. So, so with that said, as I've already noted, what we're interested in, what we're going to try to do is F equals ma. And let me begin by giving you a little bit of a qualitative statement about the F equals ma part. So as shown here, there's a little cube of material, which in this case is part of a spindle. So there's a bunch of microtubules piercing that little cube. And what I want to do is I want to look at the 6 faces, and I think I misspoke in an earlier vignette, and I referred to 9 faces of a cube. That's awesome. I mean, there's 9 components of the tensor, but there are definitely not 9 faces on a cube. So, misspeaking. I apologize for that. What's the injunction here? What's cool is that what we're going to do, like for example, if we want to sum all the x components of force, then what we do is we visit each face and we ask that face, what's the x component of force on your face? And so there's 6 faces, and on each one of those, the force will be different. Notice that on the blue faces here, the force is normal, because we're looking at the x direction of force, and my triad, my coordinate system, is drawn such that I have x, x1, x2, and x3. So at any rate, if I'm looking in the x1 direction, then the blue faces, the force is normal to the faces, and in the orange and the green cases, the x component of force is in the plane. So that's already kind of interesting. It hints at the fact that force is kind of a complicated idea for each little material volume element inside of the cube, and let me try to be concrete about that. So what I'm showing you here is the essence of what we intend to do. So first thing I want to say is that we're going to define this idea of the stress tensor. So the way I guess I want you to think of it is that when I write sigma ij, that's defined as the force in the I direction acting on the plane with normal in the j direction. And I should have said, this is really the force per area. Okay, that's poorly written. In fact, it's so bad, I think I don't want to write it that way. So here, this is the force per area. Force per area in the I direction acting on the plane with normal in the j direction. Okay, good. So that puts us in a position to now sum up all the forces on the x faces. So look here. So first of all, position x, y, z. So x, y, z is at the center of the cube. Or I could also write that as x1, x2, x3. I'm labeling them x, y, and z just to appeal to your perhaps comfort with Cartesian coordinates, but I'm going to turn this into ij, and where I is 1, 2, and 3. But let's just take a look at what I've written here. So this guy, this first one, is saying if I want to find the force on this face, how do? I take the stress tensor in the x direction. So x direction on the face with normal in the x direction, so that's sigma xx or sigma 1, 1. And I'm evaluating it at a position x plus delta x over 2. The reason I say that is that the width of the box, the width of each of these boxes, this width is delta x, or delta x1, or whatever, however you want to call it. This is delta x2 in this direction, and finally this is delta x3 here. So those are the dimensions of my little cube. And so if I want to know the area of that face, it's delta y delta z, the face that we were just talking about, this face. So that face has area delta y delta z. And so the total force in the x direction on that face is this expression that I've got right here. Now, by convention, the force is in the outward normal direction, and so on the face at x minus delta x over 2, the force is in negative x direction. That's the reason for this minus sign. So what you see is that I've got a value of the force on the front face and on the back face in the x direction, and similarly I can note the same thing on the y direction, shown here, and similarly for the z direction. So if I sum all the forces, so sum of all the forces in the x direction, what I find is that I'm left with sigma, now I'm going to write it as 1, 1, x plus delta x 1, x2, x3, minus sigma 1, 1, x minus, or x1 minus delta x1 over 2, x2, x3. That's multiplied by delta x2, delta x3. And then I have a corresponding example of sigma 1, 2, x1, x2 plus delta x2 over 2, x3, minus sigma 1, 2, and then x1, x2 minus delta x2 over 2, x3, and this is multiplied by delta x1, delta x3, and then finally plus sigma 1, 3, x1, x2, x3 plus delta x over 2, delta x3 over 2, minus sigma 1, 3, x1, x2, x3 minus delta x3 over 2, and that's times delta x1, delta x2. So that's the total force. Just to recap, what I've done is I've just said there's the 6 faces of the cube. On each of them, I find the force acting in the x direction. The convention is that sigma ij is the force per unit area in the I direction, acting on the plane with normal in the j direction. So if you look at what I've written down, I've obeyed that definition. Now I can, oh man, this is just very frustrating. I'm sorry. Just keep on getting kicked off. Okay, maybe this is promising. So the observation I want to make is that I could now, this thing wants to be a derivative. So I multiply it by delta x1 and divide by delta x1. This one wants to be a derivative. So I multiply and divide by delta x2. This one wants to be the derivative in the 3 direction, and I multiply and divide. And so when all the dust settles, what I'm left with is that this is equal to d sigma 1, 1 dx1 plus d sigma 1, 2 dx2 plus d sigma 1, 3 dx3 times delta x1, delta x2, delta x3. So that's equal to the force in the x direction on the box, the little material volume element, centered at position x1, x2, x3. It's really a cool expression. So I could also write this as, using summation convention, I could rewrite this as d sigma 1j dxj delta x1, delta x2, delta x3. Reminding you that the repeated j means sum over that index, which would yield the expression that I showed previously. Now here's an exercise for you. I'm not going to go through it. Sum of all the fy's is going to be equal to d sigma 21 dx1 plus d sigma 22 dx2 plus d sigma 23 dx3, once again times delta x1, delta x2, delta x3. Note, the units of sigma are force per area. So the gradient in sigma gives me a force per volume, multiplied by delta x1, delta x2, delta x3 gives me an ultimate units of force. Finally, there's an Fz, and that's of the form d sigma 3.1 dx1 plus d sigma 3.2 dx2 plus d sigma 3.3 dx3 delta x1, delta x2, delta x3. So I've got three equations, each of which tells me how to find the force in one of the three Cartesian directions. And what I need to do now is I need to balance this, or I should say that this is equal to F, so I have F equals ma. So let me add a page here, and let's keep going. So we want F equals ma, and so I know that m is rho delta x1, delta x2, delta x3, and then I'm going to introduce a new notation. So this is the what's called the material derivative. I'm going to explain that in a second, but this is equal to the acceleration. Let's just take a little aside and comment on this. So what the material time derivative is telling us, or the total derivative, is it's telling us how we can get time dependence, okay, in a flow like this. And it's subtle. So on the left-hand side, I'm showing you a case in which the fluid is static. There's no motion in the fluid, but over time, what's happening is that the temperature, in this case I'm looking at the rate of change of temperature, the temperature is changing because I'm using my flamethrower or heater or whatever, and I'm heating up the water. And so my little material volume element right here, that little material volume element, its temperature is going to change because T itself depends explicitly on time. But let's consider a different experiment or situation. Let's consider a steady state gradient. Now what I mean by that is, let's say that in the flow the temperature on the left is high and the temperature on the right is low. The point is that because my fluid is being carried along, my material volume element here is being carried along, a little while later it's going to be here, and a little while later it's going to be there. And so what that means is that even if there's no explicit time dependence, the system has no time dependence. I'm saying it's a steady state flow. Nevertheless, my material volume element, if I'm carrying a thermometer with me in that little volume element, I'm going to say, oh, it got colder because I moved somewhere in the flow where the temperature is lower. And so the total derivative captures both of those effects. So the thing I want to say, going back to this, is that when I write dv1 by dt, what I mean by that is dv1 by dt, and then plus v1, and then dv1 by dx1 plus v2 dv1 by dx2 plus v3 dv3 by dx3. Why is that? Because if I want to find out how much the velocity changed, so here's the heuristic argument. in the time delta t, the change to v1 will be, it'll be equal to dv1 by dt times delta t. That's fine. And then plus, I will have v1 delta t times dv1 by dx plus v2 by dt times dv1 by dx2 plus v3 delta t dv1 by dx3. And note, this is delta x1, this is delta x2, and this is delta x3. What do I mean by that? What I mean is that that's how far the fluid got transported in the time delta t, in those three directions. So basically this is what you would think. In other words, if I want to find out how much a function changed when I move a distance delta x, the answer is df by dx times delta x. That's how I find out what the change is. So that's what I'm doing here. So I'm ready then to write the total balance law. Total F equals ma. So what is it? I have rho delta x1, delta x2, delta x3, dv1 by dt is equal to d sigma 1, 1, dx1 plus d sigma 1, 2, dx2 plus d sigma 1, 3, dx3 delta x1, delta x2, delta x3, etc. Implying, so I'm going to write thus, I have rho dvi by dt is equal to d sigma ij dxj. And that's our fundamental relationship. That's the outcome, and I can also write this in direct notation as rho dv vector by dt is equal to the divergence of the stress tensor. That's another way of writing this. So this is a fair amount of technical background, and we're in a part of the course, although I am giving a homework about this, we are in the part of the course where, if you haven't seen this before, I think the way I want you to think about it is that I'm your tour guide, and I'm taking you on a bit of a tour. And we're just trying to get a feel for how do we think about the motion of continua. And so I've given you the essence of force balance here. What I've told you is, I want to add up all the forces in the x direction. And the way I do that is I find the force on each of the 6 faces of my little material volume element. And then I know that has to be equal to ma. And so to do ma, I have to do this little bit of an astuce, which requires me to note that dv by dt has 2 contributions, sort of the explicit time dependence and the fact that the fluid is being entrained. And so the net result of all that is this very beautiful and quite simple expression. And I already wrote it down, but it probably went by kind of fast. Where was it? Or maybe it's down here farther. This is where I think I will end this particular vignette, which is, this is the equation that we just wrote. That is the continuum theory of force balance. So that's what we've accomplished. Now what we need to do is we need to talk about what's the stress tensor? How does stress depend on velocity? Because remember, we're trying to write an equation for velocity. That's our governing field. So we have to figure out how stress depends on velocity. Once we have that, we'll plug that into here, and that will result in the Navier Stokes equations. So that's where we are in the logical progression.